looking at a graphical representation of this organized data. It's really a graphical representation of a either frequency distribution or of a group frequency distribution. So first, let me talk about the shapes of data. So symmetrical data. So a distribution will be said to be symmetric if the lower half is a mirror image of the upper half. So this is a symmetric distribution. It will be said to be asymmetric if it is not symmetric. And so this is an example of an asymmetric distribution. There are particular types of asymmetric distributions that are important in the study of statistics. Positively skewed distributions, distributions that are skewed to the right. And so if you happen to have most of your data being small and some of your data being large, then we say that this distribution is skewed to the right, that it is positively skewed. Next, if we have a distribution where most of our data is large values, then we say that this is skewed to the left. It is negatively skewed. Please note that this is one of the major features of, well, the major ideas in statistics is that we are always looking at and trying to control the tail. And so if you look here, most students will say, oh, the important feature here is all of my data values over here. And that's true. But in statistics, what we're trying to do is control these tails. And so because we're trying to control the tail, in statistics, the important thing is to look at your tail. And so notice it says it's skewed to the right because our tail is to the right. And so this is skewed to the right. It is positively skewed because, well, if you look at the axes, positive numbers are to the right. So it's positively skewed. Similarly, this is skewed to the left because our tail is to the left. Always look for your tail. We want to control our tails. And so our tail is to the left. And again, if you look on the number line, numbers to the left are negative. So we also say that this is negatively skewed. Okay, so a histogram. So a graph consisting of bars drawn adjacent to each other are called histograms. Now sometimes, there'll be gaps because there's, well, the frequency is 0. So next to each other, except, well, obviously, if the height of the bar is 0, then it'll look like a gap. So the horizontal scale represents the classes of the data values, and the vertical scales will somehow represent the frequencies. And so IQ scores from children with low levels of lead is listed below. Let's draw the corresponding histogram. So we have here, we're going from 50 to 69, and we have a frequency of 2. So I'm going to draw. Notice I'm going to draw from the boundaries. So I'll look at my class boundaries. My lower class boundary, 49.5. My upper class boundary, 69.5. And my height, in this case, will be 2. I'll have a height of 33. So they're 33 between 69.5 and 89.5. They are 35 between 89.5 and 109.5, 7 between 109.5 and 129.5, 1 between 129.5 and 149.5. And so this is my histogram. And this is how you would do it for inclusive type classes. Let me do things. Well, from now on, I'm going to show you a whole bunch of examples involving exclusive type classes. So, histogram. Let's first look at a histogram with equal class widths. So let's draw a grouped frequency histogram with equal class widths. 7 numbers between 10 and 20. So I have 7 numbers here between 10 and 20. 9 between 20 and 30. 2 between 30 and 40. And 2 between 40 and 50. Notice that this graph here looks like this distribution is positively skewed. And so my distribution is positively skewed. Let's draw a histogram with unequal class widths. So let's take these last 2 classes, combine them together. And so I have here 7 numbers between 10 and 20, 9 between 20 and 30, and now I'll take 4 between 30 and 50. So I just combine them together. So when I draw this graph for unequal class widths, it should look the same as this. It's just that this will now extend out here. So let's do this. So between 10 and 20, I'll have a height of 7. Between 20 and 30, a height of 9. But now, between 30 and 50, the frequency is 4. So I look here, the frequency is 4. It wouldn't look the same as this guy, because this height is 2. So if I look here, I'm now going from 30 to 50, rather than, well, let's see, so that the class width in this case is 20, whereas it used to always be 10. So I've doubled this, but now the height is half of what I thought it should be. So I should really say the following. So I sort of misled you when I was saying the height. Well, I did say originally it wasn't actually equal to frequencies. I just said that it was depended on their heights. It didn't depend on the frequency. The height of each bar just depended on the frequency. So now I'll tell you what it really is equal to. So the height of a bar when drawing a histogram should be the following. It should be the typical class width divided by your particular class width times your frequency. So let's redo this. So my typical class width in this case is 10. So for the first class, 10 to 20, the typical class width is 10. The particular class width for this class is 10. And its frequency is 7. 10 divided by 10 is 1 times 7 is 7. So its height should be 7. Between 20 and 30, well, obviously the class width is 10. The typical class width is 10. 10 divided by 10 is 1 times its frequency, which is 9. So the height of my bar should be 9. Lastly, my typical class width is 10 in this situation. My class width for 30 to 50, well, that's 20. 50 minus 30 is 20. So my class width for this particular class is 20. And the frequency for this particular class is 4. 10 divided by 20 is 1/2. times 4. So 4 divided by 2 is 2. Therefore, the height of the class from 30 to 50 should be 2. And that makes it look like the same way we did it when we just wrote it, when we wrote the data in a different way. Certainly, if you write the data in a different way, it should more or less look the same. And now it does. And so this is really the formula that we should use. So when looking at group frequency distributions, the height of each bar is equal to typical class width over the class width times the frequency. So now let's draw a frequency histogram for, well, this frequency distribution. 7 numbers, so 7 are at 15, 9 are at 25, 2 at 35, and 2 at 45. Well, these are just numbers. So if I just draw this at the number 15, it'll just look like a little line. So I want it to be a little fatter. So if I look here, the distance between 10 and 15 is the distance between 15 and 25 is 10. And so I should have the width of this as being 10. So let's make each of the widths here 10, having the center being centered at 15. And so I have here 15, 25, 35, 45, having heights 7, 9, 2, 2. So 7, 9, 2, 2. And I'll make them wider so that these bars join up and meet each other. And so this should have a class width of 10, and the middle being centered at 15, 25, 35, and 45. So really what I've done is I've made each of these into classes where these are class marks, and these are now made into classes, in which case they'll look like these. Notice that the class marks for these are 15, 25, 35, 45, and these same frequencies. And so what I've done here is I've just made these, I've made each of these classes with these particular values being my class marks. So the objective is not simply to construct a histogram, but to understand something about the graph. When graphing normal distribution, it will have a bell shape. The frequencies increase from a maximum and then decrease. They're symmetric. The left half looks like a mirror image of the right half. So let's look at IQ scores. So if I look at my IQ scores, they have the following histogram. And so they more or less have this type of shape. And so this looks bell-shaped. It looks symmetric. So it looks roughly like a normal distribution. The center is here. That's 89.5, so around 90. The variation is here. Let's see if I can see these numbers. That's 10, so it's around 20. So it's around 15 to 20. I'd say it's about somewhere between 15 and 20. Oh, they're doing the whole length. So I'm doing half of it. They're doing the whole one. So the variation is 30. Okay. So they're going from here to here, which is 30. Or if you go from here to here, it's about 15. Oh, and it says, are there any outliers? So there does not seem to be any particular data that's far away from the majority of the data. It seems to be nicely spread out. A distribution is skewed if it is not symmetric and it extends more to one side than the other. So data is skewed to the right if it has a longer right tail, also called positively skewed. Data is skewed to the left, negatively skewed, if it has a longer left tail. So this is normally distributed. This is a uniform distribution. This is skewed to the right. This is skewed to the left. There are visual ways of determining if particular data is normally distributed. And so one of the ways that we'll be looking at is to tell if some data is normally distributed is by using what's called the normal quantile plot. And so if the points are reasonably close to a straight line, and there's no obvious pattern, then we say that it looks that it's a normal distribution. It is not a normal distribution if the points are not reasonably close to a straight line or they show some systematic pattern. So this looks reasonably close to this straight line. So this is a normal distribution. It's actually this guy up here. So yeah, it looks like a normal distribution. This one here is not a normal distribution. It does not look like it's on the line. It's this one here. And so no, this does not look like it's on the line. Whereas this one here is also not normal. Notice how it goes up, down, how it oscillates. So notice this oscillating behavior. So the fact that it keeps oscillating means, well, it looks symmetric. So that looks pretty darn symmetric, but it looks oscillatory. And so if you look at this, it's this guy here. So this is actually a normal quantile plot for a uniform distribution. So those are always a little hard to distinguish because they're symmetric, but they don't look uniform. And so they don't look normal. They in this case, there's this weird pattern going on here. A bar graph. So a bar graph is very similar to a histogram. And so a bar graph will use bars of equal width to show the frequencies for categorical, qualitative, discrete data. And so I have here two numbers, and so 2 3s, 3 4s, 2 5s, and 1 6. So I have 2 3s, 3 4s, 2 5s, and 1 6. And so that is a bar graph. Now, sometimes to distinguish, and so you should draw the bar graph with these gaps in between. We say that this is a bar graph without continuity correction. If we try to make these, fatter and fatter until finally they joined up, and so now they look like a histogram, then we'll call this a bar graph with continuity correction. And so basically what we've done is we have considered each of those pieces of data as being class marks for particular classes. In this case, the class width is 1. And so, to figure out what each classes are, well, for the lower class width, a lower class limit, it's just the class width, the class mark minus h over 2, and the upper class limit will be the class mark plus h over 2. So, in this case, we'll take this class mark. Notice the class width is 1, so I'll add 1/2 and subtract 1/2 from each of these class marks. And so I'll get the classes 2.5 to 3.5, 3.5 to 4.5, 4.5 to 5.5, 5.5 to 6.5. Okay, so, and that's how we got something looking like this. Okay. Draw the frequency bar graph of discrete data and interpret, and I guess I should say, and this is a very important statement, we will use continuity correction when approximating a discrete distribution by continuous distribution. So this is a technique that we're going to be using often, especially in chapters 5 through 9. So this idea of continuity correction, we'll be going over that over and over again. The fact that we'll try to make these discrete distributions look like a continuous distribution. So, draw a frequency bar graph of the discrete data, interpret the histogram as symmetric or skewed. So I have the following. I have 1, 7, 2 8s, 2 9s, 7 10s, 18 11s, 8 12s, 5 13s, 3 14s, 2 15s, and 2 16s. So I have 1 7, 2 8, 2 9s, 7 10s, 18 11s, 8 12s, 5 13s, 3 14s, 2 15s, and 2 16s. And so this is what my bar graph looks without continuity correction. Now, if your data is indeed discrete, you should draw it looking like this with these gaps to say that, oh yes, this is discrete data. We're counting. This looks symmetric. So this distribution is symmetric. Sometimes we will draw multiple bar graphs. So we'll have more than one set of bars when we are comparing, well, 2 or more data sets. So let's say this is the median income during the years 1950 to 60, 70, 80, 90, 2000, and 2010. And these are thousands of dollars. And so, $2,000, $1,000 per year. And then, so these blue bars are for males, and the ones on the right, the pink bars, are for the females. And so males make, 32,000, females like 20,000. Okay. So that